There is a place in space where you could scream for 1 trillion years and never disturb a single atom. Right now, as you breathe, you are surrounded by 25 million trillion molecules in every cubic centimetre of air. But in the space between galaxies, that same volume contains exactly 1 hydrogen atom. 1. The silence there is so complete that light travels for millions of years without touching anything, not a speck of dust, not a whisper of gas, nothing. And this isn't rare. This is normal. 99.9% of the universe is exactly this empty. But here's what will destroy your sense of reality. We're going to visit places that make even this emptiness seem crowded. Distances so vast that our fastest spacecraft, travelling for the entire age of the universe, wouldn't even reach the starting line. Voids so enormous they swallow entire galaxy clusters like pebbles. What you think you know about space is about to be annihilated. If you're ready to have your cosmic perspective shattered, hit subscribe, because the journey ahead will leave you questioning everything. Prepare for a journey through distances beyond comprehension. We begin. Look up. On a clear night, far from the glow of any city, the sky above you looks alive. It breathes with light. Stars crowd the darkness from horizon to horizon, and if you let your eyes adjust long enough, the Milky Way itself appears a soft, luminous river of ancient light pouring across the dome of the night. It feels full. It feels generous. It feels like the universe is offering itself to you in one long, unbroken display of abundance. That feeling is a lie. Not a cruel lie. Not an intentional one. But a lie built into the very way human eyes and human minds were designed to work. We are creatures of pattern. We find signal in noise, shape in shadow, presence in the faintest flicker of light. Our brains were never built to understand emptiness at scale. They were built to survive on a small, warm, densely packed planet, where things are close together, where distances are walkable, where the world fills your field of vision in every direction you turn. And so when we look at the night sky and see those thousands of points of light, our brains do what they always do: they connect the dots. They build a picture of a universe that is full. But here is the truth, delivered slowly, because it deserves to land with its full weight. Everything you have ever seen, touched, tasted, smelled, or measured, every mountain, every ocean, every atom in your body, every star you have ever looked at, every galaxy ever photographed by any telescope ever built, all of it, combined, accounts for less than 5% of the total content of the universe. Less than 5%. The other 95% is made of things we cannot see, cannot touch, and cannot directly detect. Dark matter, a substance that has mass and exerts gravity, but emits no light whatsoever, makes up roughly 27% of the universe. Dark energy, a force or property of space itself that is driving everything apart at an accelerating rate, accounts for roughly 68%. We know these things exist not because we have seen them, but because without them, the physics simply does not work. The galaxies spin too fast. The universe expands too quickly. Something is out there holding things together and pushing things apart, and we have given it names without truly knowing what it is. That is the first layer of the lie. The universe is not made of stars and light. It is made overwhelmingly of things we do not understand. But even within that 5% of visible matter, the stars, the gas, the dust, the planets, the galaxies, even there, the lie continues. Because that 5% is not spread evenly across space like butter across bread. It clumps. It gathers. It threads itself into long, thin filaments and knotted nodes like foam on the surface of an ocean, and between those threads and nodes, there is nothing. Vast, spherical regions of space containing almost no matter at all. Regions so empty that a single cubic meter of that space might contain, on average, just one lonely atom. One atom. In a cubic meter of space. Compare that to the air in the room where you are sitting right now, where a single cubic centimetre contains roughly 27 million trillion molecules, and you begin to feel the first tremor of what true emptiness actually means. The points of light in the night sky are not evenly distributed. They are gathered, like survivors around fires, in small warm clusters within a cold and indifferent darkness. And those clusters, those galaxies, are themselves separated by distances so large they make the word large feel embarrassed to be used. When you look at the night sky and see what appears to be a sea of stars, you are actually looking at the exception. You are looking at the rare, the unusual, the clustered minority of matter that managed to find itself, that managed to collapse and burn and shine. The vast majority of the universe surrounds those points of light in silence, in stillness, in a darkness so complete and so total that no eye, no telescope, no instrument we have ever built has been able to find anything inside it. Here is another way to feel this. If you were to shrink the observable universe, the full sphere of everything we can possibly detect, down to the size of Earth, the Milky Way galaxy would be smaller than a single grain of sand. A single grain. And that grain of sand would be surrounded in all directions by more empty space than you could fill with grains of sand, even if you gathered every beach, every desert, every ocean floor on this planet and turned it all to dust. That is the scale we are dealing with. And yet, even knowing this, the lie persists. Because our brains are stubborn. Because light is seductive. Because beauty is persuasive. We look at photographs taken by the Hubble Space Telescope or the James Webb Space Telescope photographs showing thousands of galaxies in a patch of sky the size of a grain of sand held at arm's length, and we think, look how full it is. But those photographs are long exposures, sometimes hundreds of hours of collected light from billions of years of cosmic history, compressed into a single image. They are not what space looks like. They are what space contains, distilled and displayed in a way that was never meant to represent the experience of actually being there. If you were placed randomly somewhere in the observable universe, truly randomly, at any point in the vast three-dimensional sphere of everything we can detect, the probability that you would find yourself anywhere near a galaxy is extraordinarily small. The probability you would find yourself near a star is smaller still. The probability you would find yourself near a planet like Earth is so vanishingly tiny that it barely qualifies as a number. You would almost certainly find yourself in the void, in the dark, surrounded by nothing in every direction, for distances longer than the human mind can hold. That is the real universe. Not the poster, not the photograph, not the sky on a clear night. The real universe is mostly empty, mostly dark, mostly silent, and mostly made of things we cannot see. The night sky is a window, but it is a very small window, and it shows you only the most dramatic, most luminous, most unusual parts of what is out there. The rest, the overwhelming, suffocating, magnificent rest, is waiting just beyond the frame. And we are about to walk into it. We will start, as all honest journeys must, close to home. Because even here, even in the small warm neighbourhood of our own solar system, the distances are already beginning to say something that should make you pause. Something that the light from those familiar stars has been quietly whispering all along. Space is not full. Space is not friendly. Space is not built to a human scale. It never was. Most of us learned about the solar system from a diagram. You have seen it. The sun sits at the centre, warm and yellow and dominant. Then the planets line up in a neat row, each one a comfortable distance from the next Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Maybe Pluto at the end, depending on which version of the diagram you grew up with. The whole thing fits on a single page, or a single screen, or a single wall of a classroom. It looks manageable. It looks like something a person could understand in an afternoon. That diagram is perhaps the single most misleading image in the history of science education. Not because it is wrong about which planets exist, or in what order they orbit, but because it is catastrophically wrong about scale. The distances between planets in that familiar diagram are compressed so dramatically, so ruthlessly, that the image bears almost no relationship to the actual experience of space within our own solar system. If you drew the solar system to true scale, if you placed the Sun as a circle 1 metre in diameter, Earth would be a tiny dot roughly 107 metres away. That is already the length of a football field. Neptune would be over 3 kilometres from your Sun. And Pluto, small and cold and distant, would sit somewhere between 5 and 7 kilometres away from that 1 metre circle. 5 to 7 kilometres. For a diagram that used to fit on a single page. Let us sit with some real numbers now, because the numbers here are not just impressive, they are genuinely disorienting, even when you know them. Light travels at approximately 300,000 kilometers per second. It is the fastest thing in the known universe. Nothing with mass can reach it. Nothing has come close. And yet, when light leaves the surface of the Sun, it takes 8 full minutes to reach Earth. 8 minutes at 300,000 kilometers per second. That alone should give you pause. The Sun feels close. On a summer afternoon, you can feel it on your skin from 150 million kilometers away. But light, travelling faster than anything we know, needs 8 minutes to make that crossing. Now consider Pluto. On average, Pluto sits about 6 billion kilometers from the Sun. Not million, billion. Light takes just over 5 hours to travel from the Sun to Pluto. 5 hours. The same light that crosses from the Sun to your eyes in 8 minutes needs an entire working day to reach the outermost recognised dwarf planet of our solar system. If you tried to have a conversation with someone standing on Pluto, if such a thing were possible, every single word you sent would take 5 hours to arrive. Their reply would take another 5. A single exchange of sentences would consume an entire day. And we sent a spacecraft there. New Horizons launched in January 2006. It was the fastest spacecraft ever launched from Earth at that time, leaving our planet at roughly 58,000 kilometers per hour. That is a speed so far beyond anything a human body has ever experienced that it almost sounds fictional. At that speed, you could circle the entire Earth in less than 45 minutes. You could travel from New York to London in less than 4 minutes. New Horizons took 9 years to reach Pluto. 9 years of travel at a speed no human has ever felt, crossing a distance that still lies entirely within our own solar system. When it finally arrived in July 2015, the spacecraft had approximately 30 minutes of optimal data gathering time as it flew past. 30 minutes. 9 years of travel for 30 minutes of science. The team on the ground had spent years preparing for those 30 minutes. And then it was over, and New Horizons continued outward, into the dark, carrying its instruments and its golden record of humanity into a space too vast to feel. But here is what almost no one fully absorbs when they hear that story. Pluto is not the boundary of the solar system. Not even close. Beyond Pluto, beyond the flat disk of planets and dwarf planets and debris that most people think of as the solar system, lies a structure called the Oort Cloud. It is not a disk. It is a sphere, an enormous spherical shell of frozen objects, comets, icy bodies, ancient remnants from the formation of the solar system that surrounds the Sun in every direction like a hollow bubble of ice and stone. Current estimates place its inner edge at roughly 2,000 to 5,000 times the distance from Earth to the Sun. Its outer edge may extend up to 100,000 times that distance, which works out to approximately 1 full light year from the Sun. 1 light year. The boundary of our own solar system is 1 light year away. We have never seen the Oort Cloud directly. Not once. No telescope has ever resolved it. No spacecraft has ever visited it. We know it exists because of the comets that occasionally fall inward toward the Sun, long-period comets, with orbits that take thousands or even millions of years to complete. Those orbits trace back to the Oort Cloud, and from those trajectories we have built our models. But models are not measurements. The Oort Cloud, the true outer shell of our home system, remains entirely theoretical in terms of direct observation. And now consider Voyager 1. Launched in 1977, nearly 50 years ago, Voyager 1 is the most distant human-made object ever built. As of now, it sits approximately 23 billion kilometers from Earth. That number sounds enormous. It is enormous. And yet, at its current speed, Voyager 1 would need somewhere in the region of 30,000 years to fully traverse the Oort Cloud and exit the solar system entirely. 30,000 years. When Voyager 1 finally clears the boundary of our own solar system, the home system, the neighborhood, the place where we live, our current civilization, will have had to survive for longer than all of recorded human history multiplied many times over. That is the solar system. That is home. And there is something quietly devastating about this. If you let it settle, we tend to think of the solar system as a place we understand, a place that belongs to us in some meaningful sense. We have sent probes to every major planet. We have landed rovers on Mars. We have dropped a probe into the atmosphere of Jupiter. We have flown past Saturn and gazed at its rings. We feel, in a certain light, like we know this place, but the solar system extends far beyond everything we have touched, far beyond everything we have seen, into a cold and unreachable darkness that our fastest machines cannot cross in any human lifetime. The planets we know so well, the ones in the diagram, the ones with names and colours and storm systems we have photographed, they occupy only the innermost fraction of the total volume of this system. The rest is silence and ice and distance that our civilization has barely begun to think about crossing. Here is one fringe thought worth holding for a moment. Some astronomers have proposed, only half-jokingly, that the Oort Cloud may be so large and so full of objects that it technically overlaps with the Oort Cloud of nearby star systems. That at the very outermost edge of our solar system, and the outermost edge of Proxima Centauri's system, the boundaries may blur into each other, a kind of invisible handshake between neighbouring stars across an otherwise impossible gulf. We do not know if this is true. We may never know. What we do know is this: the solar system, just the solar system, just our one small star and its family of planets and moons and comets and frozen debris, is already so large that it humbles every machine we have ever built and every timescale we have ever imagined. And this is still home. This is the friendly part. Beyond the Oort Cloud, the real journey begins. There is a place where the sun's warmth finally dies, not suddenly, not like stepping from a lit room into darkness. But slowly, degree by degree, across billions of kilometers, until the heat that once forged planets and boiled oceans becomes nothing more than the faintest whisper, a mathematical abstraction, a rounding error in the calculation of temperature. Out there, at the very edge of what we might still call home, the sun is no longer a disk. It is a point. Brighter than the other stars, yes, but no longer the dominant feature of the sky. No longer the center of everything. Just another light in the dark. This is where the Oort Cloud lives. It is named after Jan Oort, a Dutch astronomer who, in 1950, proposed its existence based on something curious he had noticed about comets. Some comets, the ones we call short-period comets, swing around the sun every few years or decades, travelling in predictable orbits that stay relatively close to the plane where the planets live. But others, the long-period comets, arrive seemingly from nowhere, plunging inward toward the sun on wildly tilted orbits that take thousands, sometimes millions of years to complete. Where were they coming from? Where had they been? Oort suggested that far beyond the planets, far beyond anything we had observed, there must exist a vast reservoir of frozen objects, a cloud of primordial debris left over from the birth of the solar system. Occasionally, the gravity of a passing star, or the slow tug of the galaxy itself, would nudge one of these frozen bodies out of its stable orbit, sending it tumbling inward toward the sun. By the time we saw it, glowing and trailing a tail of sublimated ice, it had already travelled for millennia across distances we could barely imagine. He was right. Or at least everything we have learned since suggests he was right. But we have never actually seen the Oort Cloud. Not one object. Not one photograph. Not one direct measurement. Every single thing we know about it comes from inference from tracing the orbits of those long-period comets backward, from building mathematical models of how the solar system formed, from calculating where the gravitational influence of the sun finally becomes too weak to hold anything in a stable orbit. The Oort Cloud exists, we are nearly certain, but it exists in the same way that dark matter exists as an explanation, a necessity, a placeholder for something real that we simply cannot see. Here is what we think it looks like. Imagine a sphere, not a disk, not a ring, but a true three-dimensional sphere surrounding the sun in all directions. Its inner edge begins somewhere around 2,000 astronomical units from the sun. 1 astronomical unit, 1 AU, is the distance from Earth to the sun, roughly 150 million kilometers. So the inner edge of the Oort Cloud is 2,000 times that distance. Already we are far beyond Pluto, far beyond Neptune, far beyond anything resembling the familiar solar system. The outer edge, according to current models, may extend as far as 100,000 AU, which is nearly 2 light-years from the Sun. At that distance, you are closer to Proxima Centauri than you are to home. Inside this enormous shell, trillions of objects drift in the cold. Most are small fragments, rubble, icy stones no larger than a car or a house, but some may be much larger. Dwarf planets. Rogue worlds. Objects that formed in the early chaos of the solar system and were flung outward by the gravity of Jupiter or Saturn or some other giant, exiled to this frozen edge where they have circled in silence ever since. There is even speculation not mainstream, but persistent that a 9th planet may be hiding out there. Not Pluto. Something larger. Something with enough mass to subtly disturb the orbits of distant objects in ways we have observed but cannot yet explain. It has been called Planet 9, or Planet X, depending on who you ask. No one has found it. every search has come up empty, but the mathematics keep suggesting that something is out there, pulling gently on the fabric of orbital space in a way that does not quite add up unless you add another world to the equation. Maybe it exists. Maybe it is simply an artifact of incomplete data. Either way, the idea that our own solar system might still contain an undiscovered planet, not a small one, but something with real mass, real presence, says something quietly astonishing about just how much of our own neighbourhood remains unknown. The objects in the Oort Cloud do not orbit the Sun the way planets do. Planets follow relatively neat circular paths around the Sun, all moving in roughly the same direction, all staying close to the same plane. But the Oort Cloud is chaotic. Objects there travel in every possible direction, up, down, sideways, at wild angles to the solar disk. Their orbits are so long and so slow that they are barely orbits at all. They are drifts, long, lazy arcs through the dark, taking millions of years to complete a single loop. And they are profoundly alone. At those distances, the space between individual objects is measured in billions of kilometers. If you were standing on one of those icy bodies, assuming you could stand, assuming there was anything to stand on, you would see nothing nearby. No neighbours, no siblings. Just the Sun, a distant bright point, and the stars, all around you, equally distant, equally cold. You would be technically inside the solar system, but you would feel no connection to it. Gravity would hold you in a loose theoretical orbit, but you would be functionally adrift in interstellar space. Here is the uncomfortable thought that sits at the centre of this section. The Oort Cloud is still ours. It is still part of the solar system, still bound to the Sun by gravity, still composed of material that came from the same ancient cloud of gas and dust that formed Earth, that formed you. And yet it is so distant, so cold, so unreachable, that we may never visit it. Not in your lifetime, not in your children's lifetime, not in the lifetime of any recognizable human civilization. The edge of home is a place we will likely never see. And that edge is not a sharp line. It is a gradient, a slow fade. A region where the definition of solar system becomes more philosophical than physical. At what point does the Sun's gravity become too weak to matter? At what point do we stop calling something ours and start calling it the space between stars? There is no clear answer. The Oort Cloud does not end. It simply thins and fades, and eventually blurs into the faint gravitational territory of the next star over. Some models suggest that the outermost objects in our Oort Cloud may actually overlap with the outermost objects in the Oort Clouds of nearby stars, at the very fringe of the Sun's influence and the very fringe of Proxima Centauri's influence. There may be a no-man's land where frozen bodies drift in orbits that technically belong to both stars, or neither. A kind of shared wilderness, a boundary that is not a wall but a smudge. We do not know if this is true. It may be impossible to ever confirm. What we do know is this. The Oort Cloud is a reminder that even the systems we call home, even the star we orbit and the gravity well we live inside, extends far beyond our reach. It is a boundary made of ice and silence and time, and it separates the knowable from the unknown in a way that no amount of technology has yet been able to cross. Beyond the Oort Cloud, the next star waits. And the distance between here and there is where the real horror begins. Proxima Centauri is the closest star to our Sun. It sits 4.2 light-years away. That sentence is easy to say, easy to type, easy to read. But it is one of the most quietly devastating facts in all of astronomy, because hidden inside those numbers is a distance so large, so alien to human experience, that even after you learn what it means, even after you do the math and stare at the result, your brain will continue to reject it. Not because you are incapable of understanding, but because understanding this distance requires you to abandon almost every instinct you have about what the word distance means. Let us start with the unit itself. A light year. It sounds poetic. It sounds almost gentle, like something you might name a ship or a song. But a light year is not a measure of time. It is a measure of distance specifically, the distance that light travels in one full year. And light, as we have already established, moves at 300,000 kilometers per second. That is fast enough to circle the Earth more than 7 times in a single second. Fast enough to reach the moon in just over 1 second. Fast enough that if you could somehow ride a beam of light leaving the surface of the Sun, you would pass Earth in 8 minutes and reach Pluto in just over 5 hours. Now let light travel at that speed 300,000 kilometers every second for an entire year. Do not stop. Do not slow down. Just keep moving, second after second, minute after minute, day after day, for 365 days straight. At the end of that year, you will have travelled approximately 9.5 trillion kilometres. That is 1 light year. And Proxima Centauri, the absolute closest star to us, the nearest neighbouring point of light in the entire sky, is 4.2 of them away, roughly 40 trillion kilometres. If you tried to write that number out in full 40 million, the zeros alone start to lose meaning. Your eye skips over them. Your mind treats them as decoration. But every single one of those zeros represents a factor of 10, a 10-fold expansion of a distance already too large to picture. Here is one way to feel it. Remember New Horizons, the spacecraft that took 9 years to reach Pluto, the fastest object ever launched from Earth at the time of its departure, screaming away from our planet at nearly 58,000 kilometers per hour? If we pointed that spacecraft directly at Proxima Centauri and let it travel in a straight line at its current speed, without stopping, without slowing, without running out of power or breaking down or drifting off course, it would take approximately 70,000 years to arrive. 70,000 years. The Roman Empire, one of the most dominant civilizations in human history, existed roughly 2,000 years ago. It rose, it flourished, it collapsed, and its ruins are still standing. 70,000 years ago, modern humans were just beginning to migrate out of Africa. We had not yet invented writing. We had not built cities. We had not discovered agriculture. If you launched a probe toward Proxima Centauri at any point in recorded human history during the height of Egypt, during the construction of the pyramids, during the Bronze Age or the Stone Age, or the invention of fire itself, that probe would still be travelling. It would not even be halfway there yet. No machine we have ever built could make that journey within a human lifetime. Not even close, not within 100 human lifetimes. You would need technology so far beyond anything we currently possess that it might as well be magic propulsion systems that do not exist, energy sources we have not discovered, materials that can survive decades or centuries of exposure to radiation and micrometeorite impacts without degrading. And even if you solved all of those problems, even if you built the perfect starship, you would still be dealing with time itself as an enemy. Because at the speeds we are capable of now, interstellar travel is not a journey. It is a multi-generational exile. There is a concept in science fiction called a generation ship. The idea is simple, or at least the idea sounds simple. You build a vessel large enough to support a small population, hundreds or thousands of people. You stock it with food, water, air recycling, power generation, everything needed for a self-sustaining ecosystem. Then you launch it toward another star, knowing that the people who leave Earth will never see the destination. Their children will not see it either, nor will their children's children. The ship becomes a world unto itself, and the people aboard it live entire lives in transit, passing down the mission like an inheritance until, generations later, their distant descendants finally arrive at a star their ancestors only dreamed of. It sounds romantic in theory. In practice, it is a nightmare of engineering, biology, sociology, and psychology. How do you maintain a closed ecosystem for thousands of years without collapse? How do you prevent genetic bottlenecks in a small population? How do you keep a culture focused on a mission that no living person will ever see completed? These are not small problems. They are civilization-scale problems, and we do not have answers to most of them. And that is just to reach the closest star. The space between our Sun and Proxima Centauri is not merely empty. It is a kind of emptiness that defies human navigation. There are no landmarks, no rest stops, no planets to visit along the way, no moons to orbit, no asteroids to mine for resources. It is just void-cold, radiation-soaked, silent void stretching in every direction for distances that make the size of the solar system look like a puddle. If something went wrong halfway to Proxima, if an engine failed, if a system broke down, if the ship lost power or trajectory, there would be no rescue. No one could reach you. You would be 2.1 light-years from Earth and 1 light-years from Proxima, alone in a darkness so complete that even light from the nearest stars would take years to arrive. You would drift, slowly, until your air ran out, or your heat ran out, or time itself simply ran out. And your signal, your final message home, travelling at the speed of light, would take over 2 years to reach Earth. By the time anyone heard you, you would already be gone. This is the space between stars. Not the glamorous version, not the version with warp drives and hyperspace and convenient shortcuts through the fabric of reality. The real version, the version that actually exists. A gulf so vast that it has kept every star, every system, every potentially habitable world in the galaxy isolated from every other one for the entire history of the universe. There is a phrase sometimes used in discussions of interstellar travel, the tyranny of the rocket equation. It refers to the fundamental problem of propulsion, that the faster you want to go, the more fuel you need, but the more fuel you carry, the heavier your ship becomes, which means you need even more fuel to accelerate that mass, which makes you heavier still. It is a vicious cycle, and it places hard limits on how fast any chemical or even nuclear rocket can realistically travel. Some scientists have proposed alternatives: solar sails that catch the pressure of sunlight, fusion engines that burn hydrogen harvested from space, laser-pushed probes accelerated to a fraction of light speed by enormous arrays of ground-based emitters. Some of these ideas might work in theory. Some might even be buildable within the next century or two. But none of them change the fundamental truth. The stars are far, almost impossibly far, and the space between them is not a road. It is an ocean, and we are standing on the shore, looking out across a distance we were never built to cross. Proxima Centauri is right there. The nearest star, the closest possible destination, and it might as well be on the other side of the universe. So we arrive, at last, at the nearest star. After 70,000 years of travel, after generations lived and died aboard a vessel that has become the only world they have ever known, after crossing an abyss of darkness so profound that every instinct screams this journey was impossible, we arrive. The ship's instruments lock on to Proxima Centauri. The star grows larger in the viewport, and for the first time in millennia, the descendants of those who left Earth see a sun that is not their own. But it is not the sun they imagined. Proxima Centauri is a red dwarf. It is small, dim, and angry. Where our sun is a stable golden furnace burning through hydrogen at a steady, reliable pace, Proxima is a flickering ember. It has only about 1/8 the mass of our sun, and it produces only about 0.17% of the sun's luminosity. If you replaced our sun with Proxima Centauri, the Earth would freeze solid within days. The sky would darken, the oceans would turn to ice. Even at noon, the light would be a deep blood-red twilight, barely enough to see by. And yet, Proxima Centauri is not alone. It is part of a triple star system, a gravitational family of 3 suns bound together across the darkness. The other 2 members are Alpha Centauri A and Alpha Centauri B, both larger and brighter than Proxima. They orbit each other closely, locked in a cosmic dance that takes about 80 years to complete. Proxima, by contrast, is the distant cousin. It orbits the AB pair at an enormous distance, so far out that its orbital period is estimated to be over 500,000 years. Some astronomers have even questioned whether Proxima is truly bound to the system at all, or whether it is simply passing through on a long, slow trajectory that will eventually carry it away into the dark. For now, though, it remains a small red star, dim and cold, circling 2 brighter siblings from a distance so vast that they might as well be strangers. And orbiting Proxima, impossibly, is a planet. Proxima b. Discovered in 2016 using the radial velocity method, watching for the tiny wobble in the star's motion caused by the gravitational tug of an orbiting world, Proxima b is roughly 1.3 times the mass of Earth. It orbits its star once every 11.2 days, far closer than Mercury orbits our Sun. But because Proxima Centauri is so dim, so cool, that close orbit places Proxima b directly within the habitable zone, the narrow band of distance where temperatures could, in theory, allow liquid water to exist on the surface. Liquid water. The ingredient we associate with life, the substance that defines habitability in almost every model we have built. For a brief, wonderful moment after the discovery, the news felt almost like destiny. The closest star to our Sun, the nearest possible destination for humanity's first interstellar journey, hosts a planet in the habitable zone. A world where water might flow. Where an atmosphere might exist, where life, perhaps, might have found a way. But that hope does not survive contact with the details. Proxima Centauri is a red dwarf, and red dwarfs are not gentle stars. They are unstable, violent, and deeply hostile to anything fragile enough to call itself alive. Proxima, in particular, is known for producing powerful stellar flares, sudden, explosive releases of energy that flood the surrounding space with X-rays, ultraviolet radiation, and charged particles. These flares are not rare. They happen regularly, sometimes multiple times per day, and when they do, the star's brightness can increase by a factor of several hundred within minutes. Now imagine you are standing on the surface of Proxima b. The sky above you is dominated by a star that appears enormous, far larger than the Sun appears from Earth, because you are orbiting so much closer. That star is a deep, sullen red, casting everything in a dim, rust-coloured glow. The landscape is shadowed and strange, lit by a light that feels more like late evening than midday. And then, without warning, the star erupts. The sky flares white. Radiation pours down onto the surface in a flood X-rays, gamma rays, high-energy particles stripping atoms from molecules, shattering chemical bonds, ionizing the atmosphere if there even is one. If you were unprotected, you would be dead within seconds. If the planet has an atmosphere, it is being blasted away, molecule by molecule, layer by layer, eroded by the relentless bombardment. If there was ever water on the surface, it is either frozen in the shadows or boiled away by the radiation. This is not a place where life thrives. This is a place where life is actively, repeatedly sterilized. And even if, by some miracle, life did manage to emerge on Proxima B, perhaps deep underground, shielded by kilometers of rock, sustained by geothermal heat rather than starlight, it would remain forever trapped. A civilization that evolved there would look up at a sky filled with deadly radiation and realize, perhaps with a kind of quiet despair, that they could never leave. Not safely. Not easily. The very star that gave them warmth would also be their prison. There is also the question of tidal locking. Proxima B orbits so close to its star that it is almost certainly tidally locked, meaning one side of the planet always faces the star, while the other side is locked in permanent darkness. One hemisphere baked under an angry red sun, the other frozen in eternal night. The only potentially habitable zone would be a narrow ring around the edge, the terminator, where day meets night, where temperatures might be moderate enough for liquid water to survive. But even there, the winds would be catastrophic. The temperature difference between the day side and the night side would drive storms of unimaginable violence, as air rushes from the scorching light into the freezing dark and back again in endless howling cycles. Some scientists have speculated that a thick enough atmosphere might redistribute the heat, smoothing out the temperature extremes and making the planet more hospitable. Others suggest that any atmosphere thick enough to do that would have been stripped away by stellar flares long ago. The debate remains open. We do not have the tools yet to directly observe the atmosphere of Proxima B, if it even has one. We can only model and guess and hope that future telescopes will give us better answers. There is a concept in astrobiology called optimistic pessimism, though it is not an official term. It describes the recurring experience of discovering something that sounds like good news: a planet in the habitable zone, a moon with liquid water beneath its ice, a chemical signature that might indicate biological activity, only to learn, upon closer examination, that the conditions are far harsher, far stranger, and far less welcoming than we initially hoped. Proxima B is a textbook example. It is the closest exoplanet we know of. It is in the habitable zone. It is rocky, roughly Earth-sized, and orbiting a star we could, in theory, reach if we solved every engineering challenge standing in our way. It should be the perfect candidate for humanity's first interstellar colony, the first new world we set foot on beyond our own solar system. But it is also a radiation-blasted, tidally locked, atmosphere-stripped rock, orbiting a violent red dwarf that flares without warning and would kill anything soft or fragile that dared exist on its surface. It is a broken promise, a destination that looks right on paper and wrong in every other way. And yet, we cannot stop thinking about it, because Proxima B is there. It is real. It exists, and it is the closest we have to another Earth within reach, even if that reach requires technology we do not possess, and a journey that would span millennia. Even if we arrived and found nothing but silence and stone and radiation. The fact that the nearest potentially habitable planet is this hostile tells you something important about the universe. It tells you that habitable does not mean hospitable. It tells you that the conditions required for life are rare, fragile, and easily destroyed. It tells you that Earth-stable, shielded, blessed with a calm yellow star and a protective magnetic field, and an atmosphere that has remained breathable for billions of years, is not the default. It is the exception. And Proxima b, broken and beautiful and utterly unlivable, is a reminder that the universe does not owe us a second home. We have only ever had one. Step back now. Far back. Leave Proxima behind that small, violent star and its broken planet. Leave the triple system of Alpha Centauri spinning in the dark. Pull your perspective outward, away from individual stars, away from the scale where single points of light still have names and coordinates and histories. Rise above the local neighbourhood, above the bubble of space we have measured and mapped, until you can see the Milky Way not as a collection of stars, but as a single, unified structure. From this distance, it looks full. A glowing spiral, arms sweeping outward from a bright central bulge, dust lanes threading between rivers of light. Photographs taken by telescopes show it as dense, luminous, magnificent, a cosmic metropolis of stars packed together in elegant formation. You see it rendered in textbooks and documentaries, always beautiful, always brimming with presence. And the numbers seem to confirm this impression. The Milky Way contains somewhere between 200 and 400 billion stars. Some estimates push even higher. Billions upon billions of suns, each one a furnace of light and heat, each one potentially surrounded by planets, moons, asteroids, comets. How could something with that many stars be anything other than crowded? But here is the truth that those images never quite communicate. The Milky Way is approximately 100,000 light-years across. Some newer measurements suggest it might be closer to 200,000 light-years in diameter when you include the faint halo of older stars that surrounds the main disk. Let us use the smaller number for now, 100,000 light-years from edge to edge, and within that vast disk, those 200 to 400 billion stars are not packed together like grains of sand or drops of water. They are scattered, spread thin, separated by distances that make the word neighbour feel like a joke. In our region of the galaxy, the quiet outer arm where the Sun sits, the average distance between stars is roughly 4 to 5 light-years. Some stars are closer, some are farther, but on average, each star is separated from the next by a gulf of empty space measuring trillions upon trillions of kilometers. If you were traveling between stars at the speed of light, the fastest speed physically possible, you would spend years crossing nothing. Just darkness. Just silence. Just the occasional hydrogen atom drifting past like a ghost. Now multiply that emptiness across 100,000 light-years. The Milky Way is not a city. It is not a crowd. It is a sparse, thin scattering of lights across a void so enormous that even with hundreds of billions of stars, the dominant feature of the galaxy is still the space between them. Here is where this becomes viscerally strange. In roughly 4 billion years, the Andromeda Galaxy will collide with the Milky Way. This is not speculation. This is observation. We have measured Andromeda's velocity. We have tracked its trajectory. It is moving toward us at approximately 110 kilometers per second, and gravity is pulling it closer with every passing moment. Eventually, long after human civilization as we know it has either transformed beyond recognition or vanished entirely, the two galaxies will meet. The word collide sounds violent. It sounds catastrophic. You imagine stars smashing into each other, planets torn apart, solar systems obliterated in cosmic impacts that release unimaginable amounts of energy. You imagine destruction on a galactic scale. But that is not what will happen. When Andromeda and the Milky Way collide, the probability that any two stars will actually hit each other is so low it barely qualifies as a probability. Stars are too small, and the spaces between them are too large. Even as two entire galaxies pass through one another, hundreds of billions of stars from each galaxy interpenetrating, overlapping, occupying the same region of space almost nothing will touch. The galaxies will flow through each other like ghosts. Stars from Andromeda will slip between stars from the Milky Way, passing within light years of each other perhaps, but almost never close enough to interact directly. The gravitational fields will distort, orbits will shift. Some stars will be flung outward into intergalactic space, exiled from both galaxies by the chaotic tug of overlapping gravity wells. Others will spiral inward, eventually feeding the supermassive black holes at the centers of both galaxies as they merge into a single, larger black hole. But direct collisions? Star hitting star, sun smashing into sun? Virtually impossible. This is what it means for a galaxy to be made mostly of nothing. You can take two galaxies, each containing hundreds of billions of stars, and pass them directly through one another, and the stars themselves will barely notice. The collision happens at the scale of structure and gravity and the slow reshaping of orbital dynamics. But at the scale of individual, stars the scale where planets exist, where life might arise, the event is almost invisible. Galaxy collisions are, in the most literal sense, the flowing together of emptiness. There is something deeply disorienting about this. We are used to thinking of collisions as events where things touch, where surfaces meet, where matter interacts with matter in ways that produce heat, sound, light, destruction. But in space, especially on the scale of galaxies, a collision is not a physical event. It is a gravitational one. Two structures passing through each other, influencing each other, reshaping each other, without ever making contact in any meaningful sense. And this tells us something essential about the galaxy we live in. From the inside, the Milky Way feels local. We see stars scattered across the night sky. We map constellations. We name the nearest neighbours and measure their distances. We think of ourselves as living inside a structure, surrounded by other stars, embedded in something dense and coherent. But the truth is that we are not surrounded. We are isolated. The nearest star is over 4 light-years away, a distance so vast that no human-made object has ever crossed even a fraction of it. The next nearest is farther still, and the one after that, farther again. We live in a galaxy of 200 billion stars, and yet we are, in every practical sense, alone. Some scientists have calculated what percentage of the Milky Way's volume is actually occupied by stars, not the space around stars, not the gravitational influence of stars, but the physical volume of the stellar objects themselves. The number is so small it barely registers. If you could somehow remove all the stars from the Milky Way and compress them into a single dense sphere, that sphere would occupy less than 1/trillionth of the galaxy's total volume. Less than 1/trillionth. The rest is emptiness. Vacuum, interstellar medium, mostly hydrogen, some helium, trace amounts of heavier elements, all spread so thin that you could scoop up a cubic meter of space and find, on average, less than 1 atom inside it. The Milky Way is not a thing. It is an arrangement of almost nothings across a structure made mostly of void. And yet, it is home. It is the largest structure we can claim any connection to. Every human who has ever lived was born here. Every star we have ever seen with the naked eye belongs to this galaxy. Every exoplanet we have discovered orbits a star within this disk. The Milky Way is the stage on which all of human history has unfolded, and it will remain the only stage we perform on for the foreseeable future perhaps forever. But it is a stage built mostly of absence. There is a thought experiment worth holding for a moment. Imagine you could somehow place a human being at a random location inside the Milky Way's disk, not near a star, just randomly, anywhere within the volume of the galaxy. What would they see? Darkness, almost total darkness. No nearby sun to light the surroundings. No planets. No asteroids. No dust clouds glowing faintly in reflected starlight. Just the distant cold pinpricks of stars scattered in every direction, none close enough to provide warmth, none bright enough to cast shadows. The Milky Way itself, that glowing band of light we see from Earth, would still be visible, a faint arch stretching across the sky. But it would be even dimmer than it appears from our planet, because there would be no atmospheric scattering, no light pollution, nothing to amplify its presence. You would be inside the galaxy, technically, but you would feel no connection to it. You would be floating in a void, surrounded by distant lights that might as well be painted on the dome of the sky for all the difference they make to your immediate experience. That is the Milky Way. That is the reality of living inside a galaxy. It is not the poster. It is not the spiral of light. It is the emptiness between the lights. And the emptiness is almost everything. The Milky Way is not a simple disk. That is what most people imagine when they think of our galaxy, a flat, spinning circle of stars rotating smoothly around a central point like a cosmic record player. The diagrams in textbooks reinforce this image. The photographs taken from our perspective inside the disk show a band of light stretching across the sky. And we interpret that band as evidence of flatness, of symmetry, of something orderly and comprehensible. But the Milky Way is nothing like that. It is a structure, a complex, layered, violent, ancient architecture of different populations of stars, different ages, different chemistries, different motions, all overlapping and intersecting in ways that took astronomers decades to even begin mapping. It is not one thing, it is many things, nested inside one another, each with its own history and its own fate. Let us start at the centre. At the very heart of the Milky Way, buried beneath layers of dust and gas so thick that visible light cannot penetrate them, sits a supermassive black hole. We call it Sagittarius A, pronounced Sagittarius A star. It has a mass of approximately 4 million times the mass of our Sun, all compressed into a region of space smaller than the orbit of Mercury. 4 million suns crushed down into a gravitational singularity so dense that nothing, not even light, can escape once it crosses the event horizon. We have never seen Sagittarius A directly, not in the way we see stars. Black holes do not emit light, they devour it. But we have watched the stars near the galactic centre bright, massive stars that orbit the black hole at extraordinary speeds, and from their motions we have calculated the mass and position of the invisible thing they orbit. Some of those stars complete an entire orbit in less than 20 years, screaming around the black hole at speeds approaching a significant fraction of the speed of light. Their orbits are so precise, so well documented, that the scientists who tracked them were awarded the Nobel Prize in Physics in 2020. Surrounding the black hole is the galactic bulge, a roughly spherical swarm of older stars, densely packed compared to the rest of the galaxy. These stars are ancient, some of them nearly as old as the universe itself, formed in the chaotic early days when the Milky Way was still assembling itself from smaller galaxies and clouds of primordial gas. The bulge glows with a yellowish light, the combined glow of billions of aging stars, and it dominates the centre of the galaxy like a beating heart. but the bulge is not symmetrical. In the 1990s, astronomers discovered something unexpected. When they mapped the distribution of stars near the galactic center using infrared observations, infrared light can penetrate the dust that blocks visible light. They found that the bulge was elongated. Stretched, not a sphere, but a bar. A thick, straight structure of stars extending outward from the very center of the galaxy, rotating slowly as a single rigid object. This was a surprise. Not all galaxies have bars, but many do, and the Milky Way, it turns out, is one of them. The bar is roughly 27,000 light-years long, and it rotates at a different speed than the disk around it, creating complex gravitational interactions that influence the motion of gas, the formation of stars, and the shape of the spiral arms. The spiral arms. From the outside, if you could somehow leave the galaxy and look back at it, the Milky Way would appear as a classic spiral galaxy arms of stars and gas and dust sweeping outward from the central bar in elegant curving structures. There are likely 4 major arms, though some models suggest more, and their exact shape is still debated. Mapping the structure of the galaxy from inside it is extraordinarily difficult, like trying to map the shape of a forest while standing in the middle of it, surrounded by trees in every direction. What we do know is that the spiral arms are not solid objects. They are density waves regions where stars and gas are temporarily more crowded than usual. Stars move into the arms, slow down due to gravitational interactions, then move out again, like cars bunching up in traffic on a highway. The arms themselves rotate around the galaxy at a different speed than the stars, creating a persistent pattern even though the individual stars passing through them are constantly changing. We live in one of those arms. The Orion arm, sometimes called the Orion spur, a minor arm, a small branch extending off one of the major spiral structures. We sit roughly 26,000 light-years from the galactic center, neither at the edge nor anywhere near the core. Somewhere in the middle of nowhere, embedded in a flow of stars that are all slowly circling the same central black hole, completing one full orbit, roughly every 225 million years. The last time Earth was in this position in its galactic orbit, dinosaurs had not yet appeared. The next time we return here, if Earth still exists, the continents will have rearranged themselves into shapes we would not recognize, and the sun will be noticeably brighter and hotter, well on its way toward becoming a red giant. And surrounding all of this, the bar, the bulge, the disk, the spiral arms, is the halo. The galactic halo is a roughly spherical cloud of old stars and globular clusters that surrounds the Milky Way like a ghost. These stars are not part of the disk. They do not rotate in neat, orderly circles. They follow long, elliptical orbits that carry them far above and below the plane of the galaxy, plunging through the disk at steep angles before arcing back out into the darkness. Some of them are among the oldest stars in the galaxy, formed over 13 billion years ago, before the Milky Way had even settled into its current shape. Globular clusters, dense, spherical collections of hundreds of thousands of stars, are scattered throughout the halo like ancient sentinels. Each one is a relic, a fossil from an earlier era of cosmic history. Inside a globular cluster, stars are packed so tightly that the night sky, if you could stand on a planet there, would be filled with thousands of brilliant points of light, close enough that some would cast visible shadows. It would be a sky utterly unlike our own, crowded and blazing, though still separated by distances vast enough that collisions remain rare. Some of the stars in the halo were not born in the Milky Way at all. They are immigrants stolen from smaller galaxies that the Milky Way consumed over billions of years. The Milky Way is not a static structure, it is a cannibal. It grows by devouring its neighbours. tearing apart dwarf galaxies with tidal forces and absorbing their stars into its own halo and disk. Even now we can see the remnants of these meals, streams of stars stretched across the sky, tracing the orbital paths of galaxies that no longer exist. The Sagittarius dwarf elliptical galaxy, for example, is currently being torn apart by the Milky Way's gravity. Its stars are being pulled into long, thin streams that wrap around our galaxy like ribbons. In a few billion years, those stars will be fully integrated, indistinguishable from the rest of the Milky Way's population, and the Sagittarius dwarf will cease to exist as a separate entity. This is how galaxies grow, not by forming all their stars at once, but by accumulating them over time, stealing from neighbours, merging with rivals, building themselves up layer by layer across billions of years. There is something both beautiful and deeply unsettling about this. The Milky Way is not a pristine structure. It is a composite, a patchwork, a graveyard of smaller galaxies stitched together into a single coherent whole. When you look at the stars in the halo, you are looking at the survivors of dead worlds, refugees from galaxies that were destroyed so long ago that their names, if they ever had names, have been lost to time. And we are part of this. Every atom in your body was forged in a star, yes, but that star may not have been born in the Milky Way. It may have formed in a dwarf galaxy billions of years ago, lived and died and scattered its ashes into space, only for those ashes to be swept up into the growing disk of our galaxy, incorporated into a new generation of stars, one of which eventually became the Sun, around which formed the Earth, on which you now stand. Your ancestry is galactic. And it is violent. One open question that still puzzles astronomers: why does the Milky Way have the structure it does? Why a bar specifically? Why 4 spiral arms instead of 2, or 6, or none? We can model these things with computer simulations, and we can observe that many galaxies have similar structures, but the fundamental physics governing why galaxies settle into these specific patterns is still not fully understood. Gravity, rotation, dark matter, gas dynamics, all of these play a role, but the exact interplay remains mysterious. The Milky Way is old, it is complex, it is violent, and it is ours, not in the sense of ownership, but in the sense of belonging. Every star you see, every constellation, every photograph of a distant nebula glowing with the light of newborn suns, all of it exists within this single structure. The Milky Way is the largest thing we can meaningfully call home, and yet, even this immense cathedral of stars and gas and dark matter is just one galaxy among trillions, just one structure, adrift in an even larger ocean. Beyond the Milky Way, the night sky holds a secret. If you know where to look, if you find yourself under a truly dark sky, far from any city, far from any light pollution, you can see it with your naked eyes. A faint, fuzzy patch of light in the constellation Andromeda. Barely visible. Easy to miss if you do not know it is there. Most people who notice it at all assume it is a star, slightly out of focus, or a distant cloud illuminated by moonlight. But it is not a star. It is not a cloud. It is another galaxy. Andromeda, the nearest large galaxy to our own. A spiral of stars and gas and dark matter containing roughly 1 trillion individual suns, spread across a disk over 220,000 light-years in diameter. It is larger than the Milky Way, more massive, more luminous. In many ways, it is what the Milky Way might look like if viewed from the outside a grand spiral architecture, arms sweeping outward from a bright central bulge embedded in a halo of ancient stars. And it sits 2.5 million light-years away. When you look at that faint patch in the sky, you are not seeing Andromeda as it is. You are seeing Andromeda as it was 2.5 million years ago. The light reaching your eyes tonight left that galaxy when Earth was a very different place. There were no humans then, not as we understand them. Our ancestors, if you can call them, that were small, upright creatures who had not yet learnt to make tools, had not discovered fire, had not developed language or art or any of the things we associate with civilization. They lived and died under the same stars we see today, but the light from Andromeda that touches your retina now began its journey before they ever looked up and wondered what those points of light might be. This is what distance does to time. It makes the present impossible to observe. The deeper into space you look, the further into the past you see. Andromeda is not just far away in space, it is far away in time. By the time its light reaches us, everything has changed. The stars within it have moved. Some have died. Others have been born. The spiral arms have rotated. The entire structure has shifted and evolved in ways we cannot detect, because we can only ever see what it used to look like, never what it looks like right now. And Andromeda is the close one. It belongs to the same gravitational family as the Milky Way, a loose collection of galaxies called the Local Group. The name makes it sound cozy, neighbourly, like a small community of stars gathered together in the cosmic suburbs. But the Local Group spans approximately 10 million light-years from edge to edge. 10 million light-years. Even within our own galactic neighbourhood, the distances are so vast that light takes millions of years to travel between members. The Local Group contains roughly 50 galaxies, though the exact count depends on how you define the boundaries and how small a galaxy has to be before you stop calling it a galaxy and start calling it something else. Most of these are dwarf galaxies, small, faint collections of stars with evocative names like the Large and Small Magellanic Clouds, the Sculptor Dwarf, the Draco Dwarf, the Carina Dwarf. From Earth, they are invisible to the naked eye, detectable only through telescopes, but they are there, scattered throughout the Local Group like tiny islands of light in an ocean of dark. Then there are the three major players, the Milky Way, Andromeda, and the Triangulum Galaxy. Triangulum, also known as M33, is a smaller spiral galaxy about 3 million light-years away, roughly half the size of the Milky Way. It contains perhaps 40 billion stars, which sounds like a vast number until you compare it to Andromeda's trillion, or the Milky Way's 200 to 400 billion. In the Local Group hierarchy, Triangulum is the smaller sibling, orbiting the gravitational influence of Andromeda, much like the Magellanic Clouds orbit the Milky Way. All of these galaxies are gravitationally bound to one another. They are not drifting apart like most structures in the universe. Instead, they are slowly falling toward each other, pulled together by the collective gravity of their combined mass. This is why we know that Andromeda will eventually collide with the Milky Way. The collision is not a possibility. It is an inevitability, written into the motions we can measure today. But here is where the scale becomes truly disorienting. The Local Group, this family of 50 galaxies spanning 10 million light-years, is gravitationally isolated. It is an island. Beyond its edges, the nearest comparable collection of galaxies is the Virgo cluster, approximately 65 million light-years away. The Virgo cluster is much larger than the Local Group, containing over 1,300 galaxies, but to reach it, you would have to cross a gulf of emptiness that dwarfs anything we have discussed so far. This is where we encounter a new category of void. Not interstellar space, which is empty, but but still contains the occasional hydrogen atom, the occasional grain of dust. Not even the space between spiral arms within a galaxy, which is sparse but still recognizably part of a larger structure. This is intergalactic space, the space between galaxies, and it is empty in a way that challenges the meaning of the word. In the space between galaxies, the density of matter drops to roughly 1 atom per cubic meter. 1 atom in a cube of space large enough to hold a person. Compare this to the air you are breathing right now, which contains approximately 2.5 10.19 molecules per cubic centimeter. That is 25 millimillion molecules in a space smaller than your fingernail, and you begin to grasp just how profound this emptiness is. There are no magnetic fields threading through intergalactic space, at least none strong enough to matter. No dust clouds catching and scattering starlight, no gas clouds collapsing to form new stars, no comets, no asteroids, no planets, no moons. Nothing but vacuum so complete that if you could somehow travel there, the dominant source of illumination would be the cosmic microwave background, the afterglow of the Big Bang itself, still radiating through space 13. 8 billion years after the universe began. In intergalactic space, even light has nothing to interact with. Photons travel for millions or billions of years without hitting a single atom, without scattering off a single particle. They simply move through the void, carrying information from one galaxy to another across distances so vast that by the time they arrive, their source may no longer exist. This is the space that separates the local group from the rest of the universe. This is what isolates us, what makes our small collection of galaxies feel like a genuine neighborhood despite the millions of light years between its members. Because beyond the local group, beyond the gravitational bonds that hold our galaxies together, there is nothing for 65 million light years. Nothing but emptiness so pure, so absolute, that it feels almost sacred. There is something deeply humbling about this realization. The local group, our extended cosmic home, containing hundreds of billions or perhaps trillions of stars, enough worlds to sustain countless civilizations, enough raw material to build technologies we cannot even imagine, is a tiny cluster of islands in an ocean of nothing. And that ocean extends in every direction for distances that make the local group itself look small. Some astronomers have suggested that intergalactic space may not be entirely empty. Dark matter, if it exists as current theories suggest, should be present even in the voids between galaxies, though at densities so low it would be undetectable by any current method. There may be rogue stars, ejected from their home galaxies by gravitational interactions, wandering alone through the darkness. There may be primordial gas, left over from the early universe, slowly cooling and thinning as space itself expands. But even if these things exist, they do not change the fundamental truth about intergalactic space. It is a realm where the normal rules of astronomy break down, where the concepts of neighborhood, of locality, of connection lose their meaning, where the universe reveals itself not as a place full of stars and planets and the possibility of life, but as a structure built primarily of absence. The local group is our safe harbor, the only region of space where galaxies are close enough to see each other clearly, to influence each other gravitationally, to eventually merge and share their stars. Beyond its boundaries, isolation becomes the defining feature of existence, and we have not yet begun to explore what lies beyond those boundaries. We have not yet encountered the larger structures, the superclusters and filaments and cosmic voids that organize matter on scales so vast they make the local group look like a single point of light. The first silence, the emptiness between galaxies, is just the beginning. Pull back further now. leave the local group behind that small family of 50 galaxies bound together by gravity across 10 million light-years of mostly empty space. Zoom out until even Andromeda, that trillion-star spiral visible to the naked eye, becomes too small to see. Continue pulling back until entire galaxy clusters, collections of hundreds or thousands of galaxies, shrink to points of light. Keep going until the scale becomes so vast that individual galaxies disappear entirely, leaving only the faint glow of their collective presence. From this perspective, something extraordinary becomes visible. The universe has architecture. For decades, astronomers assumed that if you zoomed out far enough, the cosmos would look random. Smooth, evenly distributed. Galaxies scattered across space like salt grains spilled on a dark table, with no particular pattern, no underlying structure, no organizing principle beyond the random clustering you would expect from gravity acting over billions of years. This assumption seemed reasonable. It was even built into the standard models of cosmology. On large enough scales, the universe should be homogeneous. But that is not what we found. Instead, when we mapped the three-dimensional positions of thousands of galaxies, when we traced their motions and analysed their distributions, a pattern emerged that no one had expected. Galaxies were not scattered randomly. They were organised. Arranged, threaded together into vast, web-like structures that stretched across hundreds of millions of light-years. Filaments of matter, thin and elongated, connecting dense nodes where galaxy clusters congregated like cities at the intersection of highways. And between these filaments, enormous void regions of space containing almost nothing at all. The universe, on its largest scales, looks like foam, like the bubbles that form when you shake soap and water, creating a structure of thin films and hollow spaces. But this is foam made of galaxies instead of soap molecules, and the bubbles are hundreds of millions of light-years across. This discovery changed everything. It meant that the universe was not homogeneous, not smooth, not random. It had structure, and that structure was organized on scales so large they challenged the fundamental assumptions about how matter could arrange itself under the influence of gravity alone. Something was shaping the cosmos at distances that light takes hundreds of millions of years to cross. We call this the cosmic web. And our local group, it turns out, is just one tiny thread in a much larger tapestry. In 2014, astronomers made a discovery that redefined our understanding of where we live in this web. They had been mapping the motions of thousands of nearby galaxies, measuring their velocities, tracking the directions they were moving through space. What they found was that all of these galaxies, including our own Milky Way, were flowing in the same direction. Not randomly, not in the chaotic independent motions you might expect, but in a coordinated flow like rivers converging toward the same distant sea. They called this flow pattern Laniatea, which means immense heaven in Hawaiian. Laniatea is not a thing you can see. It is not made of stars or gas or any visible matter. It is a structure defined purely by motion, by the discovery that roughly 100,000 galaxies spread across approximately 520 million light-years of space are all moving toward the same gravitational center. That center, which astronomers have named the Great Attractor, lies somewhere in the direction of the constellation Centaurus. Hidden behind the disk of our own galaxy, invisible to direct observation, but detectable through its gravitational influence on everything around it. The Great Attractor itself is likely a massive galaxy cluster, or perhaps a collection of clusters, containing enough matter to pull our entire supercluster toward it over the course of billions of years. We are falling toward it right now, along with every other galaxy in Laniatea, at a speed of roughly 600 kilometers per second. But because of the distances involved, this journey will take far longer than the current age of the universe to complete. We will never arrive. the expansion of space itself will carry us away faster than we can fall inward, leaving the great attractor forever out of reach. But here is what makes Laniatea genuinely unsettling. It was only defined in 2014, less than a decade ago. For the entire history of human astronomy, we thought we lived in a galaxy, orbiting within a galaxy cluster, possibly part of some larger structure, but with no clear idea what that structure might be. Now we know that we are part of a supercluster containing 100,000 galaxies, all flowing toward a common centre, all bound together by gravitational currents operating on scales we had never imagined. And Laniatea is just one supercluster among many. The cosmic web is made of these structures, superclusters connected by filaments, filaments connecting superclusters, all of it arranged in a three-dimensional network that spans the observable universe. The filaments themselves are not made of empty space. They contain galaxies, gas clouds, dark matter, all the normal ingredients of cosmic structure, but stretched out into long, thin threads like cosmic highway systems connecting one major hub to another. Between the filaments lie the voids. These are not merely empty regions. They are actively empty. Regions where matter has been pulled out by the gravity of the surrounding filaments, leaving behind spaces so barren they contain only a few dozen galaxies, where thousands would be expected. Some voids are over 300 million light-years in diameter. If you were a galaxy unlucky enough to find yourself in the centre of such a void, the nearest neighbouring galaxy might be over 100 million light-years away. Your night sky would be almost completely dark. No nearby galaxies to observe, no cosmic neighbours to interact with, just profound, crushing isolation. Void galaxies, the few that do exist in these empty regions, develop differently than galaxies in more crowded environments. They have fewer opportunities to merge with neighbours, less access to fresh gas from intergalactic space, different rates of star formation. Loneliness, it turns out, changes galaxies just as it changes people. They become smaller, dimmer, more isolated, evolving in ways that reflect their cosmic solitude. But even the voids are part of the pattern. They are not random empty spaces. They are bubbles in the foam, organised and shaped by the same processes that create the filaments. As gravity pulls matter toward the filaments, it leaves voids behind not as accidents, but as necessary consequences of large-scale structure formation. The cosmic web extends as far as we can observe. Every survey, every map, every three-dimensional reconstruction of galaxy positions reveals the same underlying architecture. Filaments and voids, nodes and walls, all arranged in a pattern that somehow emerged from the nearly uniform conditions of the early universe. How smooth initial conditions gave rise to such complex structure is one of the most important questions in modern cosmology, and the answer involves dark matter, dark energy, and processes we are only beginning to understand. There is something called the end of greatness, a somewhat tongue-in-cheek term for the scale at which cosmic structure finally becomes random. Below this scale you see patterns, stars clustered into galaxies, galaxies clustered into groups, groups clustered into superclusters, superclusters arranged into filaments. But above this scale, the pattern should disappear. The universe should finally look smooth and homogeneous. The problem is that as our surveys get better, as we map more galaxies across larger volumes of space, we keep finding structure at larger and larger scales. The Hercules Corona Borealis Great Wall, for example, is a filament estimated to be over 10 billion light-years long, so large that some astronomers question whether it can be a single coherent structure at all. At these scales, the universe should look uniform. The cosmic microwave background, the afterglow of the Big Bang, shows us that the early universe was incredibly smooth, with density variations of only 1 part in 100,000. How did such small variations grow into structures 10 billion light-years long? How did the cosmic web emerge from conditions that were almost perfectly uniform? We have models. We have simulations. We have theories involving dark matter and dark energy and gravitational instability operating over billions of years. But the honest answer is that we do not fully understand how the universe built itself into the foam-like structure we observe today. The cosmic web exists. We can map it, we can measure it, we can trace our place within it. But we cannot yet explain why it looks the way it does. What we do know is this. The local group sits on a minor filament, part of the Laniakea supercluster, flowing toward the Great Attractor along with 100,000 other galaxies in a coordinated motion that will continue for billions of years. We are part of something vast, something organized, something that operates on scales so large that the entire history of human civilization represents less than a single heartbeat in its slow gravitational evolution. The cosmic web is the largest structure we know of. It is the skeleton of the universe, the framework on which everything else hangs. And it is mostly empty space. In 1981, astronomer Robert Kirshner was conducting what seemed like routine work mapping the positions and distances of galaxies in a region of sky near the constellation Boats. It was the kind of careful, methodical survey that forms the backbone of astronomy, measure the redshift of each galaxy, calculate how far away it is, plot its position in 3-dimensional space, and slowly build up a picture of how matter is distributed across the universe. But as Kirshner and his team added galaxy after galaxy to their map, something disturbing became apparent. There was a hole in the universe. Not a small gap, not a region that simply happened to contain fewer galaxies than average, but an enormous spherical void, roughly 330 million light-years in diameter, containing almost nothing at all. Where their models predicted thousands of galaxies should exist, they found perhaps a few dozen. Where the cosmic web should have been dense with matter, they discovered what appeared to be a bubble of pure emptiness, carved out of the fabric of space itself. They called it the Boats Void, though it has since earned other names: the Great Nothing, the Big Empty, the Cosmic Bubble, and it fundamentally changed how astronomers think about empty space. Because the Boats Void is not simply an absence of matter, it is a structure, an active, evolving, dynamic structure that shapes the galaxies around it, influences the flow of matter across hundreds of millions of light-years, and continues to grow even now, billions of years after it first formed. This is the paradox of cosmic voids. They are not passive empty spaces, like holes in a piece of Swiss cheese. They are participants in the cosmic web, as important to the architecture of the universe as the filaments and superclusters that surround them. Emptiness on cosmic scales becomes a force unto itself. To understand how voids work, you have to think about gravity not just as something that pulls objects together, but as something that shapes the flow of space itself. In the early universe, matter was distributed almost uniformly across space. Almost, but not quite. There were tiny density fluctuations regions that were very slightly denser than average, and regions that were very slightly less dense than average. These fluctuations were incredibly small, just 1 part in 100,000, barely detectable even with our most sensitive instruments. But gravity amplifies small differences. The slightly denser regions began to pull matter toward themselves, growing denser over time. As they grew denser, their gravitational influence increased, allowing them to pull matter from even greater distances. Meanwhile, the slightly less dense regions found their matter being pulled away toward the denser areas. As they lost matter, they became even less dense, which made it easier for their remaining material to be stolen by neighbouring overdense regions. This process is called gravitational instability, and it operates like a cosmic sorting mechanism. Rich regions get richer, poor regions get poorer. Dense areas attract more matter and become the filaments and nodes of the cosmic web. Underdense areas lose matter and become voids not through any dramatic process, but through the slow, patient redistribution of material across billions of years. The boat's void is the result of this process taken to an extreme. Over the course of roughly 13 billion years, gravity has evacuated nearly all the normal matter from this region of space, leaving behind a spherical bubble that contains perhaps 1/10 the density of galaxies you would expect to find in an average region of the universe. It is not completely empty, no void is, but it is empty enough that a galaxy finding itself at the centre of the boat's void would be over 150 million light-years from its nearest comparable neighbour. Imagine that isolation for a moment. Imagine being a civilization that evolved on a planet orbiting a star in a galaxy, drifting through the heart of such a void. Your night sky would be almost completely dark. No nearby galaxies to observe through telescopes. No cosmic neighbours to study or wonder about. The universe, from your perspective, would appear to consist of your single galaxy surrounded by infinite darkness. You might conclude that you are alone in creation, not just as a species, but as a galaxy, as a structure, as anything larger than your own stellar neighbourhood. And you would have no way of knowing that this was an illusion, no way of detecting the vast cosmic web that exists beyond your local void, the filaments and superclusters and galaxy clusters that fill the universe elsewhere. Your cosmology would be profoundly wrong, not through any failure of intelligence or observation, but simply because of where you happen to be located in space. But the boat's void is not the only such structure, nor is it the largest. Surveys of the cosmic web have revealed dozens of major voids, each one a spherical or elongated region of space where galaxies are far sparser than average. The CMB cold spot a region in the cosmic microwave background that appears slightly cooler than the surrounding area, may be the shadow of a void so enormous it challenges our understanding of how such structures can form. This hypothetical supervoid would be roughly 1.8 billion light-years in diameter, containing perhaps 20% less matter than the cosmic average. Other notable voids include the local void, which our own local group sits near the edge of, and the Capricornus void, which spans over 200 million light-years. Each one represents a vast bubble of near emptiness carved out of the cosmic web by billions of years of gravitational evolution, and these structures continue to evolve. Voids are not static. They grow over time as gravity continues to pull matter away from their centres toward the surrounding filaments. Computer simulations suggest that voids expand at a rate proportional to their size. Larger voids grow faster than smaller ones, and that this expansion continues until it is eventually halted by the accelerating expansion of space itself, driven by dark energy. Some voids may eventually merge with neighbouring voids, creating even larger empty regions. Others may be invaded by galaxies falling inward from the surrounding filaments. The cosmic web is not a fixed structure. It is a dynamic, evolving system, and voids are active participants in that evolution. The galaxies that do exist within, voids, the so-called void galaxies, provide fascinating insights into how environment shapes galactic evolution. These galaxies tend to be smaller, bluer, and more actively forming stars than their counterparts in denser environments. They experience fewer gravitational interactions with neighbours, fewer mergers, less stripping of their gas by tidal forces. In some ways, They represent a more pristine population galaxies that have evolved in relative isolation, unperturbed by the chaotic processes that affect galaxies in clusters and filaments. But they are also lonely galaxies, isolated, cut off from the flows of intergalactic gas that fuel star formation in more crowded regions. Their evolution is shaped by absence as much as by presence, by what they lack rather than what they possess. There is something deeply philosophical about void galaxies. They remind us that location matters, that context shapes destiny, that where you are in the universe fundamentally influences what you can become. A galaxy born in a void will never experience the gravitational ballet of a rich cluster. A galaxy born in a cluster will never know the profound silence of the cosmic empty spaces, and neither can choose where it begins its existence. Recent research has suggested that voids may play an even more active role in cosmic evolution than previously thought. They may influence the formation of the cosmic web itself, helping to shape the filaments that surround them. They may affect the expansion of space, creating regions where the geometry of space-time itself is subtly different from the cosmic average. Some theories even propose that voids could serve as laboratories for testing modifications to Einstein's theory of general relativity. Because gravitational effects that are too small to detect in dense regions might be amplified and observable in the profound emptiness of cosmic voids. The Boat's void and its siblings represent something extraordinary. They are proof that emptiness itself can have structure, that absence can be an organizing principle, that the spaces between things are as important to the architecture of reality as the things themselves. In a universe that is already 95% dark matter and dark energy substances, we cannot see or directly detect the discovery that even the remaining 5% is organized primarily around vast bubbles of nothing feels like a final cosmic joke. We live in a universe where emptiness has more power than matter, where the spaces between galaxies are more important than the galaxies themselves, where absence shapes presence more than presence shapes absence. The voids are not empty, they are full of emptiness. And emptiness, it turns out, is one of the most powerful forces in the cosmos. There is a telescope floating in space right now, roughly 1 million miles from Earth, that can see further back in time than any instrument humans have ever built. The James Webb Space Telescope. It sits at a gravitational balance point called L2, where the combined gravity of Earth and the Sun keeps it in a stable orbit, always positioned so that our planet blocks the heat and light that would otherwise interfere with its extraordinarily sensitive infrared detectors. It is the most powerful space telescope ever launched, with a mirror nearly 3 times the diameter of Hubble's, folded like origami to fit inside a rocket, and then unfolded in space with the precision of a Swiss watch. And when it turns its golden eye toward the deepest, darkest patches of sky regions that appear empty to every other telescope, regions where Hubble sees nothing but black, it reveals something extraordinary. Galaxies. Thousands of them. Scattered across the void like distant campfires, each one a collection of billions of stars. Each one shining with light that has been travelling toward us for over 13 billion years. 13 billion years. Let that number settle for a moment. The universe itself is approximately 13.8 billion years old. When the James Webb Space Telescope looks at the most distant galaxies it can detect, it is seeing them as they appeared when the cosmos was less than 1 billion years old, still a child, still cooling from the violence of its birth, still settling into the structures we recognize today. Those galaxies, if they still exist at all, have spent the entire history of the universe evolving, changing, perhaps merging with neighbours or being torn apart by tidal forces, or simply aging into something completely unrecognisable. but we will never see them as they are now. We can only ever see them as they were. This is the fundamental limitation of astronomy. Light takes time to travel, and distance becomes a journey into the past. When you look at the Sun, you see it as it was 8 minutes ago. When you look at Proxima Centauri, you see it as it was 4.2 years ago. When you look at the centre of the Milky Way, you see it as it was 26,000 years ago. And when the James Webb Space Telescope looks at the most distant galaxies, it sees them as they were when the universe was young, alien, and utterly unlike the cosmos we inhabit today. The early universe was a strange place. Galaxies were smaller, more chaotic, more actively forming stars. The cosmic web had not yet fully developed. Dark matter was only beginning to organise itself into the filaments and voids we observe today. The first generation of stars massive, short-lived, composed only of hydrogen and helium because heavier elements had not yet been forged in stellar cores, were still dying in spectacular supernovas, seeding space with the carbon, oxygen, silicon and iron that would eventually become planets, atmospheres, and life itself. The galaxies that James Webb observes in the deep field are not just distant in space. They are alien in time. They represent a universe in the process of becoming itself. A cosmos still figuring out what it wants to be when it grows up. And yet, even these ancient, primordial galaxies are not the edge of what we can see. Because there is something beyond them, something older, more fundamental, more universal, something that represents not just the edge of the observable universe, but the edge of observability itself. The cosmic microwave background. If you were to look even deeper than the most distant galaxies, past the time when stars were first forming, back toward the very beginning of everything, you would eventually reach a point where there are no galaxies to see. Not because they are too faint, not because they are too far away, but because they did not yet exist. You would be looking back to a time before the first stars ignited, before the first galaxies formed, before gravity had pulled matter together into the structures we associate with the modern universe. But you would not see darkness. Instead, you would see light. A faint uniform glow coming from every direction at once, filling the entire sky with radiation that has been travelling toward you for over 13.8 billion years. This is the cosmic microwave background, the afterglow of the Big Bang itself, still radiating through space like the heat from a fire that burned out eons ago. The cosmic microwave background marks the moment when the universe first became transparent to light. In the very early universe, space was incredibly hot and dense. So hot that atoms could not hold together. Electrons and protons existed separately, floating in a plasma so energetic that photons, particles of light, could not travel more than a tiny distance before colliding with a free electron and being absorbed or scattered in a random direction. The universe was opaque, like being inside a thick fog, except the fog was made of fundamental particles and the temperature was tens of thousands of degrees. Then, approximately 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into hydrogen atoms. This process is called recombination, and it happened everywhere at once, across the entire cosmos, in a transition that took perhaps a few thousand years to complete. When it was over, the fog lifted. Space became transparent. Light could suddenly travel freely across vast distances without being absorbed or scattered. The cosmic microwave background is that first light, the light that filled the universe the moment it became possible for light to travel freely. It has been redshifted by the expansion of space from visible light to microwave radiation, but it is still there, still detectable, still carrying information about the conditions that existed over 13 billion years ago. and it represents an absolute wall. Beyond the cosmic microwave background, we cannot see, not because our telescopes are not powerful enough, not because the light is too faint, but because there is no light. The universe before recombination was opaque. Any light that existed then was trapped, absorbed, scattered, unable to escape the dense plasma that filled all of space. When we observe the cosmic microwave background, we are looking at the surface of last scattering, the final moment when light and matter interacted before space became transparent. Behind that surface lies a hidden universe. 380,000 years of cosmic history that we can never directly observe, no matter how advanced our technology becomes. We can infer what happened during that time. We can build models based on particle physics and cosmology. We can study the subtle patterns in the cosmic microwave background radiation that tell us about the density fluctuations that existed when the universe first became transparent. But we cannot see it. The cosmic microwave background is not just the edge of the observable universe. It is the edge of the potentially observable universe. It is a wall made not of matter or energy, but of time itself. A boundary beyond which direct observation becomes physically impossible, not due to technological limitations, but due to the fundamental nature of how light and matter interact in an expanding cosmos. There is something profoundly unsettling about this wall. It means that no matter how far our technology advances, no matter how powerful our telescopes become, there will always be parts of cosmic history that remain hidden from us. The universe keeps its deepest secrets locked behind a barrier of opacity, accessible only through inference, mathematics, and the faint traces left in the cosmic microwave background itself. Some cosmologists have speculated about ways to peer beyond this wall. Perhaps gravitational waves which were not scattered by the dense plasma of the early universe could carry information from before recombination. Perhaps neutrinos which barely interact with matter could provide a window into the hidden epochs. These ideas remain speculative, but they represent the deep human desire to push past every boundary, to see around every corner, to probe every mystery the universe presents. For now, though, the cosmic microwave background remains our absolute horizon. When the James Webb Space Telescope looks at the most distant galaxies, it is not just exploring space, it is exploring time. Each observation is a journey backward through cosmic history, a glimpse into chapters of the universe's story that unfolded billions of years before our solar system existed. And when it reaches the limits of what galaxies it can detect, when it peers as far back as current technology allows, it approaches but never quite reaches that final wall, the moment when the universe first became transparent, when light first gained the freedom to travel unimpeded across the cosmos. Beyond that wall, the universe keeps its secrets. And it always will. There is something happening to space itself that no human civilization will ever witness, but which determines the ultimate fate of everything we can see. Space is growing, not expanding into something, not pushing against boundaries or filling empty regions that existed before. Space itself, the fundamental fabric of reality, the stage on which all cosmic drama unfolds, is stretching, creating new distance between galaxies, new emptiness between superclusters, new isolation between every structure in the universe. This is not a gentle process. It is accelerating. For the first several billion years after the Big Bang, the expansion of the universe was slowing down. Gravity was winning. The mutual gravitational attraction between all the matter in the cosmos was gradually putting the brakes on cosmic expansion, like a ball thrown upward that rises more and more slowly as Earth's gravity pulls it back down. Astronomers expected that this deceleration would continue, perhaps forever, perhaps until the expansion stopped entirely and reversed into a cosmic collapse. Then, in 1998, two teams of astronomers studying distant supernovas made a discovery that shattered every assumption about the universe's future. The expansion was not slowing down, it was speeding up. Something was driving galaxies apart at an accelerating rate, overcoming gravity, overcoming the natural tendency of matter to pull itself together. They called this mysterious force dark energy, and it appears to make up roughly 68% of the total content of the universe, more than dark matter, far more than ordinary matter, more than everything else combined. We do not know what dark energy is. We do not know where it comes from. We cannot detect it directly or measure it in laboratories. We know it exists only because of what it does. It makes space itself expand faster and faster, driving distant galaxies away from us at velocities that approach the speed of light. And here is where the horror truly begins. There are galaxies whose light is reaching us right now, galaxies we can observe with the James Webb Space Telescope. Galaxies whose stars and planets and possible civilizations we can study and wonder about that are already moving away from us faster than light can travel. This does not violate Einstein's relativity, because these galaxies are not moving through space. The space between us and them is expanding, carrying them away from us at superluminal velocities. Any signal sent from such a galaxy today, any radio transmission, any burst of light, any attempt at communication, will never reach us. Ever, the expansion of space will stretch the distance between us faster than the signal can cross it, like trying to walk forward on a treadmill that is accelerating backward faster than you can run. These galaxies are beyond what cosmologists call our event horizon. They exist, they are real. Some of them are probably filled with stars and planets and perhaps even life. But they are forever beyond our reach, forever outside our sphere of influence, forever inaccessible to any form of contact or communication. And the event horizon is moving closer. As dark energy continues to accelerate the expansion of space, galaxies that we can currently observe will cross beyond the event horizon and disappear from our observable universe. Not because they are destroyed, not because they stop existing, but because the space between us and them will grow so fast that their light can no longer reach us. First, the most distant galaxies will vanish. The ancient, primordial structures that the James Webb Space Telescope observes in the deep field will fade from view as they are carried beyond the horizon by the expansion of space. Then, progressively closer galaxies will follow. The cosmic web will begin to unravel from the edges inward as structure after structure disappears into the unreachable distance. Eventually, and by eventually, we mean in a few trillion years only the local group will remain visible. All other galaxies, all other superclusters, all other evidence that the universe was once filled with structure and light will have vanished beyond the event horizon. A future civilization arising then would look into their sky and see what appears to be a universe containing only their own small collection of galaxies surrounded by infinite darkness. They would have no way of knowing that billions of other galaxies still exist, just beyond their reach. No way of detecting the cosmic microwave background, which will have redshifted into undetectable radio waves. No way of discovering that the universe was once hot, dense, and filled with the afterglow of the Big Bang. Their cosmology would be profoundly limited, based on observations of a universe that appears almost empty, almost static, almost eternal. They would be alone in a way that no civilization has ever been alone, cut off not just from contact with other life, but from evidence that other structures ever existed. The expanding dark would have erased the history of the cosmos from their sky, leaving them isolated in a pocket of local space with no way of knowing what they had lost. This is the ultimate consequence of the distances we have been exploring. Not just that space is vast, not just that galaxies are separated by unimaginable gulfs of emptiness, but that the expansion of space itself is actively working to increase that isolation, to drive structures apart until they become permanently disconnected from one another. Even within the local group, this process will eventually have consequences. The Milky Way and Andromeda, currently approaching each other for their inevitable collision in roughly 4 billion years, will merge into a single massive elliptical galaxy. The gravitational binding energy of this merged system will be strong enough to resist the expansion of space, at least locally. But the Magellanic Clouds, the dwarf galaxies, the more distant members of the local group, some of them may eventually be carried away, lost to the expanding dark, leaving the merged Milky Way Andromeda system increasingly alone. There is something profound and melancholy about this future. The universe is not just vast and empty now, it is becoming more vast and more empty with every passing moment. The cosmic web, the filaments and voids, the superclusters and galaxy clusters, all of it is temporary. All of it is slowly being torn apart by the relentless acceleration of space itself. Dark energy does not just separate galaxies, it separates possibilities, it closes off futures. It ensures that the universe will become, over time, not just empty, but permanently, irreversibly empty, with no possibility of new connections forming across the growing voids. But perhaps there is a different way to think about this. Perhaps the horror is not in the distances themselves, but in our initial assumption that the universe should be full, should be connected, should be built to a human scale of comprehension. Perhaps the horror comes from expecting cosmic structures to behave like human communities, where proximity leads to interaction and distance can be overcome with enough effort and time. The universe was never built for us. It was never designed to be comfortable or comprehensible or navigable. It simply is. Vast beyond measure, empty beyond imagination, structured by forces we barely understand, operating on scales that dwarf our ability to visualize or travel or influence. And yet, here we are, on this small warm world, orbiting this ordinary star, embedded in this quiet spiral arm of this unremarkable galaxy. Here, where water flows and air moves and life has somehow found a way to exist, despite the overwhelming indifference of the cosmos around it. Here, where consciousness has emerged from matter, where matter has learned to think about itself, where the universe has developed eyes and minds capable of looking outward into the dark and trying to understand what they see. You are part of this story. Every atom in your body was forged in the core of a star, scattered across space when that star died, incorporated into new structures, new worlds, new forms of organization, until eventually, after billions of years of cosmic evolution, they came together to form you. You are made of starlight and emptiness and time itself, temporarily arranged into the shape of a thinking being. The distances are real. The emptiness is real. The isolation of galaxies and the acceleration of space and the eventual loneliness of cosmic structure, all of it is real. But so are you. So is this moment. So is the fact that matter has found a way to contemplate matter, that the universe has evolved minds capable of feeling wonder and sadness and connection despite the vast indifference that surrounds them. Rest now. Let the enormity of space be what it is. Let the distances be distant. Let the dark energy continue its patient work of separation and isolation. None of it diminishes the small miracle of your existence, the temporary warmth of consciousness in the cosmic cold. Sleep and dream of stars.